And like we did with addition, the first question we need to ask is, when can you multiply two matrices together?
They have the, if the left side is 4 by 3, then the right side must be like have the 3 rows.
Okay, yeah. If one matrix is 4 by 3, in other words it has 3 columns, then the second matrix would have to have 3 rows. Alright, to put it in general terms, you have to have the same number of columns in the first matrix as you have rows in the second matrix. Okay? So, for example, here we have two matrices. A is a 3 by 5 matrix and B is a 5 by 7 matrix. I can multiply these because 5 is the number of columns in the first matrix, and it's the same as the number of rows in the second matrix. Now, when you do this, the result, AB, you want to take a stab at what the result might be? What kind of a matrix might it be? Yeah, it's going to be a 3 by 7 matrix. Okay? So, the easiest way to do this is to actually write the dimensions of the matrix in your problem. The middle two have to be the same. Your result is the number of rows from the first one and the number of columns from the second one. Okay? Now, that should make better sense as to why that is once we look at the process of multiplying them. Okay? But just to get the hang of this a little bit more, take a look at C and D. First of all, can I multiply those together?
Yeah.
Yes. All right. What would CD have as its dimensions?
4 by 10.
It'd be a 4 by 10 matrix.
Can you simplify them or no? Not simplify.
What do you mean simplify?
Like 2, 5.
No, no.
Okay.
Good question. Now, notice here, we're going to actually look at one thing that's not a property, that has been a property with other types of things, and that is, if we have B times A, notice, if I tried to turn this around, in other words, what property am I trying to use here? No, the commutative. If I try to do that, can I even multiply those? No. Okay? These are not the same, so there is no solution here. It's undefined. Matrix multiplication is undefined for matrices that don't have the right dimensions. Okay? Now, as we'll see later on, even if you are able to multiply them, that doesn't mean you're going to get the same result. Okay? We'll see that when we work through our examples. Okay? Now again, just for practice, let's say I had matrix E, and it had dimensions of 1 by 6. Well, let's make it a 1 by 4. Okay? And I'm multiplying it by matrix F. Now, what are dimensions of F that would actually make it possible to multiply? 4, 2, 4, 1, 4, 3. Okay? A 4 by 2 matrix. Okay? And then our result, EF, is going to be a 1 by 2 matrix. Good. Okay? Now, as you can see, as you can see, 2 by 2 matrix. 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 we're going to get different results. Sometimes the matrices end up very large, sometimes very small. If you think in terms of the number of elements, how many elements does a 3 by 5 matrix have? 15. And a 5 by 7 has 35. Our end result, though, has 21. Okay? Now, when you do the matrix multiplication, that means you're going to have to find 21 different values. And there's a lot that could go wrong if you're not careful with your arithmetic. Alright, so just be very careful. CD is going to have 40. Alright? However, EF only has 2. Okay? So, and also, think of it like this. Let's say I had F, and it was a 4 by 1 matrix. EF would be what?
1, 1.
A 1 by 1, so it would just be a single number in brackets. Okay? However, this is one of the ones where, let's say I turn it around and I have F is a 4 by 1 times E, which is a 1 by 4.
Oh, it would it not be a 4 by 4?
FE is going to be a 4 by 4. So we'd have 16 solutions that we have to find. Okay? So again, sometimes when you try to use the commutative property, you do get something that's possible to multiply, but it's not going to give you the same solution. Okay? Alright, so let's take a look at an example here. Okay? Let's look at an example. These are the same 3 matrices that we were using in our examples yesterday with the matrix addition and all that stuff. So you already have these in your notes, most likely. But let's go ahead and try B times C. Alright? Now if I do B times C, what's my result going to be?
4, 4. BC 4, 4.
Yeah, it's going to be a 4 by 4 matrix. Alright, which means we're going to have 16 different values that we're going to need to find. Okay? So the first thing I do is I'm going to write down my 2 matrices. And then we'll start the process of finding what this product is. Now I'm going to give myself plenty of space here. Alright? Because we're going to have 4 rows. Okay? And I'm actually going to put blanks in for all the spaces. You don't need to do this, but at least when you're starting out it might be helpful so you don't forget something. So there's 4 columns and there's 4 rows in each column. Okay, so there's our matrix. Okay. And what we'll do here is, let me shrink that up just a hair. We'll show the work and then we'll also write the final solution here. Okay. So, alright, so let's talk about how we're going to find each element of our matrix when we're multiplying. So I'm going to first of all start with this element. And you'll notice this is the element that's in the first row and the first column. Alright? So that's the element that we're dealing with. So what we're going to do, remember we said there had to be the same number of columns in the first as there are rows in the second. Okay? We're going to use the first row of the first matrix and the first column of the second matrix. And we're going to multiply those together. Now, how are we going to multiply them together? We're going to do this similar to the way that we did the dot product with our vectors. Remember, we multiplied the horizontal components, we multiplied the vertical components, then we added those together, right? Here, we're going to multiply the first thing together, 1 times 7. We're going to multiply the 5 by the 3. And we're going to multiply the 6 by the negative 1. And then we're going to add those all together. Alright? So we have 7 plus 15 is 22, minus 6 is 16. Alright? Everyone with me so far? Okay? Alright. Now we will look at our second element. Okay? Now this second element is in the first row again, but it's in the second column. Alright? So here's what I'm going to do. I'm going to use the first row. You're always using rows of your first matrix, and you're always using columns of your second matrix. Alright, so first row, second column to get the element that's in the first row of the second column. Okay? So, I'm going to do 1 times 7.
I have this.
Plus?
1 times 6.
Oh, yeah, sorry. Distracted me.
Conference going global politics. It ran long.
Okay. Alright, 1 times 6 plus 5 times 2 plus 6 times negative 2. Okay? We multiply those and add them all up. 6 plus 10 is 16. Minus 12 is 4. Okay? Let's do another one. This element here is first row, third column. So again, I'm using this first row, but now I'm using the third column. Okay? So I have a 1 times 5 plus 5 times 1 plus 6 times negative 3. 5 and 5 is 10, minus 18 is a negative 8. Okay? Then, the last element in our first row, okay? First row, fourth column. Alright, so again, I'm going to use this fourth row, but now I'm going to use the fourth column. Okay? So I have 1 times 4 plus 5 times 0 plus 6 times negative 4. So 4 plus 0 minus 24 is a negative 20. Alright? So now we are a quarter of the way done with the problem. Okay? Alright, now, obviously, if we kept circling things and writing things out and all that, you know, it's going to get really, really messy. Alright, I'm not recommending that you necessarily circle things as you're doing the problem, but I just want you to see how we're pairing these things up. Okay? The nice thing about understanding it this way is that if you're asked for just a random element, let's say I ask you for the element in the second row, in the third row in the second column. All right, so we're trying to find. Let's get a different color here. No, we'll do that one. Okay, the third row, second column, right here. That's an ugly color. All right. So what row and column are we going to use from our matrices?
Third row, second column.
All right, so we use the third row and the second column to find that element. You can find an isolated element if you understand how those elements are found. Okay, third row, second column, we use the third row and the second column. So 9 times 6 is 54. 9 times 2 is 18. And 9 times negative 2 is a minus 18. So, try to get in the right spot here, that would just be a 54. Alright? So, that's the nice thing about learning the matrix multiplication this way, is that you can just pick isolated things. And actually, on the SAT or the ACT, sometimes they'll throw in a question like this. If you've taken either of those, you may have run into one. They're not going to have you do the entire matrix multiplication. They'll just say, hey, what's this term? Okay? Or this element of the solution. Alright? Take a couple minutes and see if you can't find the second row, at least. Okay? Try to find the second row, we'll check that, and then see how you did.
Set on 75 instead of 72.
Alright, so that's what you ought to get in your second row. If you didn't, take a look back and double check. Okay. You had negative 14 plus 9 minus 8 to get your negative 13. you had a negative 12 plus 6 minus 16 to get your minus 22. You have a negative 10 plus 3 minus 24 to get your negative 31. And then you had a negative 8 plus 0 minus 32 to get your negative 40.
Is there a pattern?
Okay? What do you mean, is there a pattern?
So the first one, if you subtract 12 from each one, you get the next number. And the second one, if you subtract 9. Is there like a pattern?
Yeah,
Right.
because 6 plus 5 plus 1 is 12.
There might be a pattern on this one because when I made this matrix, I just did 7, 6, 5, 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4.
Yeah, 'cause that's
So you might get a pattern in this specific example,
Right.
but that's only because how I made up the matrix.
Because 1 plus 5 plus 6 is 12. Negative 2 plus 3 plus 8 is 9. Is there.
Alright, good. Good. So any questions on the second row here? It should start cooling down here in a moment. We turn the AC down.
Thank you.
So yeah, someone bumped it up like 3 degrees from what it was supposed to
I
be.
would
So
definitely do that.
alright.
It's perfect in here.
Let's see here. So now we need third row. So go ahead and let's call out the numbers that we would use. So first of all, 9 times 7 is
63,
63 plus
47,
plus
54.
negative 9,
negative 9, and that's
81.
81.
Yeah.
Is that right? Yeah, 81. Good. Okay. So then for this element, third row, third column, 45
9,
plus 9.
negative 27,
Good. And what do we get?
27,
We get 27? Yeah, 27. 54 minus 27 is 27. Good. And how about our last column here? 36.
0, and negative 36.
Alright, so we get 0. Okay? Alright, now our last row.
Great.
Our last row,
Oh, 0,
0.
6, 8, negative 2,
Okay?
1,
Get a 1. And then we've got
0,
0.
Plus 2.
Alright, so we got a minus 2. 0 plus 1. Alright, so we got a minus 5.
0, 0, negative 8.
Good. Alright, so there you have it. Okay. Now, as you can see, there are a lot of calculations that have to be done to get this end result. Okay? Every element you're multiplying 3 times and adding twice. So there's 5 operations just to get one element of your answer. Okay? So, again, being very careful with the arithmetic is important. Alright? Any questions about what we've done here? Alright. I want to give you guys a couple minutes. We're actually going to turn this around. Okay? C times B. Now, what should our solution be?
It's opposite.
It'll be a 3 by 3. Okay? Because we have a 3 by 4 and we have a 4 by 3. Alright? Because we reversed the order, the 4s do match, so that it is possible, but now we're going to get a 3 by 3 matrix as our answer, which is kind of nice because that's only 9 elements instead of 16. Mm-hmm.
So when like solving what CB is,
Also now use
would we ever use the 4, 0, negative 4 column and the 0, 1, 2 row?
Yes. In fact, what we'll do, because it's a 3 by 3, what we'll end up doing okay, we will still use the first row and the first column. But we're going to have 4 pairs that we've got to multiply and add up. Okay? So while there are fewer elements, you're still like multiplying the same number of things and adding the same number of things. It just produces fewer elements. Okay? You just multiply those and add them together. Alright, so we do 7 times 1 is 7. 6 times negative 2 is a minus 12. 5 times 9 is a 45. And 4 times 0 is 0. So 7 minus 12 is negative 5, plus 45 is 40. That's going to be the first element. Okay? And you use the same process here. Yes? Alright? Yeah, go ahead and let's do this whole thing. See if you guys can get all of them. Alright? By the way, when you're showing your work, alright, I want to see you adding them up. You don't need to write down 7 times 1 plus 6 times negative 2. But go ahead and write down 7 minus 12 plus 45 plus 0 to show me that you're doing the process right. Okay? So if you have a quiz or a test on this, then
We need to run the process.
show your process. So your calculator actually can do it, but you want to learn our process here.
Cancel the answer for the last one. Please. 我才10多级，11级，那你们多久？我有 quiz， 我有可能就来。
Put that away and see what we're doing, please.
Mr. Wilson, how'd you get 7?
How'd you get 7?
See, second row, second column, 15 plus 6 plus 9 No. First row, second column, sorry. No, second row, first column, there we go. 3 minus 4 would be -1. Oh wait, yeah, that's 8. Sorry. There we go. -22. That should be good.
이제 100, 드려 100.
Yeah, 102.
22.
Let me see here.
Okay,
First row, second column, 35 and 18 would be 53, plus 45 would be 98, and 4, yeah, we're on 2. 3. I'm on 2. That's why you write down your
Yeah.
things. Don't try to do it all in your head.
What if they're the
Say
other way
miracle
around?
one more
What if
time.
it's what if it's B times
B times C
is the top?
is the one we did up here.
Yeah.
Okay?
So it really depends what order they're in.
Yeah, the order really matters here. Okay? Alright. Do we have them?
Wait.
Are you recording?
Alright, so, any questions about any of those elements that you couldn't quite figure out? Alright. Alright, so let's discuss real briefly here some of the properties related to matrices, okay? We already identified that matrix multiplication is not commutative. It's not commutative, which means, as we just saw, the order matters, okay? However, we do have the associative property, okay? The associative property with matrix multiplication means that if we have three matrices multiplied together, it doesn't matter if you do the first two and then the last one, or if you multiply the second two and then multiply that by the first one. Okay? As long as you don't change the order at all, it'll still be okay. Looking at that briefly just with the dimensions, let's say A is a 3 by 5 matrix, B is a 5 by 2 matrix, and C is a 2 by 4 matrix. Okay? If I did A and B first, what am I going to get? It's going to be AB is going to be a 3 by 2 matrix. And then if I multiply that by C, that's a 2 by 4, what do I get?
3, 4.
ABC is a 3 by 4 matrix, okay? Now that's not necessarily proper notation there, but after you multiply those together, the result is going to be a 3 by 4 matrix, okay? Now, what if we did it? What if we did it in using the associative property? We did the B times C first, okay? B times C is going to give us
5 by 4.
a 5 by 4 matrix. And then, what do you end up with? Yeah, once you multiply A by B and C, you get a 3 by 4 matrix.
So
Same thing.
the only thing we can do is A times C.
Yeah, you can't do A times C and then try to throw B in. It's not like real numbers. But as long as you keep the order the same, you can do it in whatever order you want. Okay? Now, this isn't a proof of it. I'm just showing you what the dimensions, our dimensions would stay consistent. Okay? One question you might have is, well, what if the dimensions don't work out? Okay? Well, then no matter how you do it, the dimensions won't work out right. Okay? For example, if, let's say C was a 3 by 4 matrix, okay? Then when you tried to do what you got with A and B times C, you would get something undefined. You'd get no solution. Alright? If you did that up here, the nice thing about doing it this way is that you find out that there's no solution one step earlier. Okay? Because if you try to do these, you're going to get no solution. So it doesn't matter what A is. Okay? So, even if there's no solution, the associative property would show that. Okay? So. Now, number 2 up here. We have the distributive property, however, you have to be careful to keep the order. Notice we have left distributive property and right distributive property. If we're distributing from the left of our parentheses, then we need to distribute it and keep it to the left of each of the terms we're distributing it to. Okay? Now again, with real numbers it didn't matter. But with matrices, since it's not commutative, it does make a difference. Okay? So A times the quantity B plus C is AB plus AC. However, if you have A plus B in parentheses and that's times C, when you distribute C in, you have to distribute it in after the A and the B.
Oh, so when you calculate A plus B first, then times C.
You could do that. Alright, now it may
Distribute
be possible that you can't add A and B. Let's say their dimensions are different. Okay? However, both of them could multiply with C. Like, for instance, on this one, you could have A as a 3 by 5 matrix, B is a 5 by 2 matrix, and C is a 5 by 3 matrix. You can't add these together because they're not the same dimensions, but if you distributed the A to both of them, 5 and 5, 5 and 5, you could actually do the multiplication. Okay?
But after the distribution, we still cannot put them together.
You couldn't put them together into one matrix. No, your solution would just be 2 matrices added together. See ya. Have a good game. All right. And the same thing would apply with the right distributive property. Okay.
And
Sorry, Ellie?
Does the example have that solution?
In this case, yes, because when you got down to here, the 2 and the 3 were different. Okay. Here, the 2 and the 3, you had different ones.
Is there a way to tell?
Actually, yeah. I mean, if you just look at them, even without parentheses, okay, those are the same, so that would be possible, but these are different, so that's not possible. However, if you look at it the way it was originally, you know, these are the same, so that's possible. These are the same, so that's possible. And actually, we can tell what our result's gonna be too.
3,
3 by 4.
Could you do like 3A times 2B or something?
Yeah, you could do that. You could do 3A times 2B. And all you would do is actually that kind of takes us to number 4. The associative property when we have a scalar instead of another matrix. And the difference here is that you can move that scalar around wherever you want. In fact, if you had this, you could multiply A by 3 and B by 2, or you could take that 6 out and do the AB first and then multiply the whole thing by 6.
Am I gonna do that?
No, we're not going to do that for time, just for time's sake. Okay, so there are a lot of things, and that's what you have to be careful with. Anytime you're dealing with something new, like in this case we're dealing with matrices, you have to be careful that the things that you used to do with real numbers still apply. Here we find the commutative property doesn't work, but the associative property does. The distributive property does, but only if you're careful to keep the order in the same order, alright? So, the last thing I want to mention here, I just want you to be able to see, is the identity. Anytime you have multiplication, there's always an identity. And in matrices, that's no different, okay? The identity matrix is what's called a square matrix, alright? That means the length, or the rows and columns are the same number, alright? Notice what it is. It's full of zeros except for across the diagonal you've got all ones. And that looks kind of familiar, right? Row reduced echelon form, if you think about it, we had that, and then our answers as a fourth column. Well, if you just looked at that, that's the identity matrix for 3 by 3. Okay? Alright, we'll let you guys go. Have a good day.